We usually think of time travel as science fiction, but you, me, and our traveler here, Arjun, are actively moving through a flexible physical dimension right now. Over a century ago, Albert Einstein proposed his theory of relativity. He showed that space and time are permanently stitched together into a single fabric. Because of this connection, the universe enforces a strict rule on velocity. As a physical object moves faster through space, its passage through time actively slows down. Time is not a universal background clock ticking at a constant rate for everyone. It is a physical dimension that bends and stretches depending on how fast you move. This bending happens right above our heads. A GPS satellite orbits Earth at 9,000 miles per hour, making its clock tick slightly slower. But Earth's gravitational pull is weaker at this high altitude, which actually causes time to speed up. When physicists combine these two effects, the weaker gravity wins out. GPS satellite clocks experience time at a rate slightly faster than 1 second per second. NASA scientists and engineers must use strict mathematical formulas to correct this daily time dilation. If they didn't, the navigation apps on your phone would fail within hours, placing you miles away from your actual location. Traveling forward into the future is a proven engineering reality, but traveling backward into the past presents a severe theoretical challenge. This diagram illustrates a Minkowskian time travel spacetime. It models how traveling around a dense singularity bends time backward. Notice how the hourglass-shaped light cones tip horizontally near the center. This reverses an object's trajectory, allowing a traveler to encounter their past self. General relativity mathematically allows for these closed loops, but sending a person back to meet themselves sets the stage for a severe clash of logic if they interfere with their own history. Imagine a consistency paradox. Our traveler goes back a few minutes and physically stops his past self from entering the time machine. If he never enters the machine, he can never go back to stop himself. To prevent these impossible contradictions, physicists look to Stephen Hawking's chronology protection conjecture. He proposed that the laws of physics possess an automatic defense mechanism. If a traveler attempts to alter a past event, the mathematics of the universe force the probability of that interference to equal exactly zero. This is known as the rule of self-consistency. In physical reality, this zero probability means any attempt to change the past will simply fail. The environment forces a mechanical accident, a weapon jams, or the traveler simply slips. Classical physics acts as an impenetrable enforcer. It perfectly protects the timeline, ensuring that a history that has already happened remains intact. That strict enforcement works perfectly at the macroscopic scale of classical physics. But if we shrink down to the subatomic scale, quantum mechanics provides a mathematical backdoor. Physicists have developed a framework called the Entangled Timelines Model, or ECTC. It uses the many worlds interpretation, the idea that all possible quantum outcomes physically exist, to bypass the classical barriers. This diagram visualizes how the model works. When a time machine interacts with its environment, it becomes quantum entangled. Instead of overwriting the past, the traveler's actions physically birth a separate, parallel reality. Under these rules, paradoxes disappear. Quantum mechanics resolves the contradiction by isolating the dangerous interference into a completely disconnected universe. Relativity smoothly allows us to travel forward, stretching time through speed and gravity. Meanwhile, the mathematics of quantum mechanics offer a path backward, but only by stepping off our original timeline entirely. We inhabit a universe governed by strict, unbreakable rules. We are permitted to stretch, bend, and manipulate time, but we are absolutely forbidden from creating logical contradictions. Time is not a rigid straight line that we are trapped on. It is a complex, navigable landscape.